Welcome back, chemistry fans. Today, what we are going to do is a brand new unit, something called the mole. But before we get into what the actual mole is, we need to build our background knowledge. We've kind of alluded to this on many occasions. It is called the molar mass. It's intimately related to the atomic mass. So let's jump into this. Once we understand this concept, we can then move into what a mole is. All right, so remind you that we have a periodic table, and on your periodic table, there are individual boxes that represent the elements, and they have what we called some atomic masses. But it depends on what periodic table you use as to how many digits there are for those atomic masses. So we need to come to some understanding of how we're going to regulate this variability. And this is called significant figures. Significant figures are numbers that have actually been measured. Whenever you do measure, there's always usually one estimated digit after this. So in the case of this one, we don't know if that's a 6, in this example of this pencil, we don't know if that's actually a 0.7 or if that's a 0.6 or a 0.8. It's an estimation. So, but you always have to give it one more estimate, because it wouldn't be accurate for us to just say, oh, it's 7, because we know it's not. It's somewhere in between. So you have to give it a best guess. Now, there are some rules that go along with significant figures as far as how we count them then whenever you are presented with a value. There are 4 of these rules. The first rule says that all numbers are going to be counted as significant. In other words, if you have a 1, 2, 3, 4, 5, 6, 7, 8, 9, those are real numbers. They are significant. So in the case of numbers zeros, however, there's a few rules that we have to understand about those. If the zeros are trapped in between real numbers, they also count as significant. So in this first example, there are 1, 2, 3, 4, 5, 6 significant figures. Now, as far as whenever we are counting with significant figures, whenever there is zeros in front, they are never significant, because we can alter that number and turn it into 1, 2, 3, 4, 5. We can turn that into a scientific notation, and no longer do those zeros are they apparent? Are they appearing? So they are not significant. They are merely placeholders, but they are not measured values. They can be eliminated. The same thing is true for zeros at the beginning, even if there are zeros at the end. So these zeros at the beginning, they'll never count. But if there's zeros at the end, they will count as long as there's a decimal, because I can change this one into scientific notation, 1, 2, 3, 4 to the -4. The zeros at the end have actually been measured, and I understand your argument is that they don't change the value, so why should we write them? Because they have been measured, and that's what we're writing down, are an account of what has actually been measured. Now, if, however, there is no decimal point, those zeros are also eliminated, because this is an estimate. And so it goes back to the idea of giving an estimation of how much money is in your bank account. You could estimate, but it's unlikely that you know the exact amount. Like myself, I could say, oh, there's about $100 in my bank account. If I went and looked, there's probably somewhere closer to $105.43. So the difference is this only has one number that I am confident about. This one, because I looked, has all 5 numbers that are confident. That's the rules about sig figs. Now, how do you apply them whenever you are dealing with multiplication and addition? They have 2 separate rules. Addition, you take the lowest number of digits after the decimal. When you multiply, you take the lowest number of digits anywhere that they occur. So when we add these examples here, notice I have 1, 2, 3, and I have 1. So my answer can only have 1. So in the second one with subtraction, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, we go with the lowest. So my answer should have 1, 2, 3, 4 digits. However, when we multiply, the rule changes, and we must know significant figure counting rules. So zeros in front do not count. There are 2 digits, and that's why I only have 2 digits in my answer. You're saying, no, you have all those other ones. Remember, zeros in front do not count because we can turn this into a scientific notation to the -4. Now, the second one, as I am dividing 1, 2, 3, 4, 5, 1, 2, 3. So my answer can only have 3. Don't forget to round when you cut off numbers. Okay, so with that said, now we're ready to start venturing into our ideas about molar mass. Every element I alluded to earlier has an atomic mass associated with it on the periodic table. Some of them have different numbers of significant figures. You go with what is provided to you and use that number of significant figures for your calculations. So how are we going to utilize those figures, those values? You are going to create something called a molar mass. A molar mass is the sum of all the weights in a molecule. So it's not an atomic mass, which is associated with an atom. It's the molar mass, which is associated with a molecule. So for the example of water, there are 2 H's. So that means I need to add together the 2 weights of hydrogen. There is only 1 oxygen. So whenever we add these together, notice how many significant digits there are after the decimal. With the oxygen, there's 1, 2, 3, 4. With the hydrogens, there are 1, 2, 3, 4, 5. So our answer should have 4 significant figures. This 8 needs to round up. So my final answer should be 18.0153 grams. All right. And then 2 more examples here. I've got hydrochloric acid, HCl. How many digits does it have? Oh, by the way, it's just 1H, 1Cl. So I've got 1, 2, 3 digits after the decimal, 1, 2, 3 digits, 1, 2, 3 digits in my answer. Everything worked out okay. For glucose, the formula is C6H12O6. What we need to do is we need to distribute the 6 to the weight of the carbons, distribute the weight 201. What is carbon? 1, 1. Sorry, 0, 1, 1, not 0 right there. So that's a 1, 1. And so we'll distribute 6 carbons, 12 hydrogens, and 6 oxygens. And then they come up with these weights, the 72 for the carbons, 12 for the hydrogens, and 96 for the oxygens. Once you add those together, we get this weight of 180.1446, but we're only allowed to use 3 significant figures. So therefore, we cut off the 6 and it rounds the 4 into a 5 to get my final answer. Doing a couple more examples, again, because it's obvious that I've already done them. Let's do this. Now, on each one of these examples, what we are doing is we're just simply adding up their weights. So, got 1 moles of each one of these materials. So, neon on the periodic table, it looks like it has a weight of 20.18. My units on this one, grams. Sodium, it is element number 11, 22.99 grams. But oxygen, be tricky, is O2. So even though it's only 1 amount of this, it is going to be O2. So it's 2 times 15.9994, which means your weight is going to be 31.9988. H2O, we already did previous example. CO2. So I've got 1 carbon at 12.011. I've got 2 oxygens. And we just figured out that that's 31.9988. I add those together. And what you get is 44.0098. However, because this is an addition problem, we must use significant figures, 1, 2, 3 digits, 1, 2, 3 digits. It rounds that up. So my final answer is actually 44.010. Methane, CH4. I've got my carbon is 12.011. My hydrogens are 1.00794, and there are 4 of those hydrogens. 4 plus 12.011, and you get 16.04276, but that can't be our answer. With significant figures, we can only use 1, 2, 3 digits. The 7 has rounded that 2, so my answer is 16.043 grams. Okay, this is everything that I wish to share with you for the first topic in Unit 3. Thank you so much for listening. Hope that it's easy for you. Practice, practice, practice.